Thank you very much. It's a pleasure to be here and to be able to talk to you, and a pleasure to be invited to be here. And I'm really electrified. As you see, there is even some cable, some microphone, and so on. So it's also a first-time experience for me. So in addition to this video that they produce here, I additionally do some private recording. So I have to be very careful in what I say, because every word will be remembered for minutes. Okay, let's start. So we are constructivists here, we are proof theoreticians, we are real number guys, and I'm essentially a real number guy. And so I work with real numbers, and especially I do implement them, and I do this already since 20 years now. And still, I'm able to improve my implementation significantly, which means it was a very dumb initial version, and now it's a little bit better. And then we got an idea from interval community using Taylor models. I will give you some examples and, of course, very few closing remarks. Let's start with real numbers. So we'll need this later on. I hope you all know this. Otherwise, I will be too fast. I hope you all know this. So what do we do with real numbers? How can we represent them? One thing would be we can represent them using open intervals. Okay, we don't want to have double precision intervals, so we use some, let's say, dyadic endpoints to do this. And then we come to some I standing for intervals, some set of intervals with not rational, not dyadic, but somewhere in between dyadic endpoints. We want to compute with them, so we need a computational model, which could be the Oracle Turing machine. So a function Oracle Turing machine like Carrico did it. You have the Turing machine model. The Turing machine has some oracle, some black box. It can query the box, can get answers, and it itself gets some questions and can answer. And this means we have something going from queries to answers or from inputs to outputs, which means we have essentially some word functions. Input is a word, output is a word, or interpret it so it can be read simpler. The input could be natural numbers. The output could, for example, be intervals. So we are working with sequences of intervals. And from these sequences of intervals, we go to the real numbers in the way like Klaus Weyrauch did it in his book and in his work since almost 40 years. And we represent a number by a sequence of intervals in the following way. It's not exactly how he did it, but it's the idea behind that. We have the intervals. The intervals have to shrink if we continue with our computation. The intervals have to shrink to a diameter of 0, which means they go to a point. We don't have that they intersect, so it could be non-intersecting intervals, which would be bad. So additionally, we demand that it's intersecting intervals, and then they shrink to a single point. So converging to a single point, that's the idea behind that. And then, of course, this oracle would be the real number. We ask for precision and get an interval which might be small, it also might be large. We just know it will converge. Then we have functions on top of that. So if we have such a real number and we apply a function, which means a computable function, which means we apply an Oracle Turing machine, then we get, again, a structure which is of the same thing. So this outer blue box, we may ask it some question about intervals, and we will get some outputs, which are intervals. It may ask its argument sometimes, but the resulting blue box should be the value of the function at the point x. Okay. This is the background, and from this we get to representations. And this is a diagram for representations. We start on, let's say we compute, or the theory of computation is here on the sequences. The intended computation is here on the real numbers, and we translate with some representations from the lower level to the higher level. And of course, we want to sell this, like Andre said, we want to address human people. That is, we should hide as much as necessary and possible. So we can hide all this crazy stuff below, hide it, and just keep the necessary things, which is we work on real numbers. And they have to be continuous. This is not a problem for all of us, but maybe a problem for other people who don't know about continuity, but at least someone, let's go back, someone who is doing some implementation should have an idea of what is continuity. They usually won't have an idea of what is constructive mathematics or something like this. So we have to reduce things. Okay, this was the Oracle Turing machine level. We want to go to some real computation. So we need some implementation of real numbers on real computers. So again, we address humans, so the real numbers should be some abstract data type, and there are real numbers, and they are not, we should not think of them as streams or something like this, but they are atomic objects. It's hard to look inside. We don't want to look inside. So close at hand, we have sequences of intervals representing real numbers. So take any favorite language, like Haskell, OCaml, C++, Java, whatever you want to do, and implement sequences. It's different style of programming in all of these languages, but implement the sequences such that the diameter goes to 0, and knowing that the diameter goes to 0, and they concentrate on a single point. Okay, this is what we want to have, and then there are many implementations, and at least 3 or 4 people of this community are with us, or more than 3 or 4 are here who did similar things.
Yeah, I think it's 5.
Oh, more than 4, even 5. Okay. So my favorite example, and I will come back to this many times in this talk, it's the logistic map, a simple dynamic system. We start with some initial value, and we do a simple iteration, and we have some value C, and this C could be even rational, could be a simple value. It's already complicated enough. And then the values jump. If you have a close look, they jump between 0 and 1. They never leave this interval. If we start with something between 0 and 1, they jump. And depending on the constant C, for example, if you start with 3.3 and you start here, you jump there, you jump here, there, and you will converge to 2 points in a certain way. So there is an orbit of 2 points that you converge to, this point and this point. So this is easy. In this area here, it's a little bit more complicated. It's quite chaotic what's happening. Okay, it's quite chaotic what's happening, so let's try to compute it. So to compute it, we need some specific values. Let's start with 0.5 and have a constant of 3.75, both rational. We only do rational computations here, or we could do rational computations here. I warn you, don't do this. You won't get far. We want to compute the values. The values are depicted in this diagram, and we want to compute it in our favorite language. My favorite language is C++. So this would be some program a beginner could write for this problem. And if we do this, we have the values there. They are behind the blue ones, so you don't really see the difference, what's there. But the question is, how did I get the red, so the red ones are the double. How did I get the blue ones? I simply changed. We have real numbers now. Okay, I changed it to real numbers, and now we have a look. What's the difference between the two of them? And here you see the difference. So more or less with double precision numbers, you compute noise. Okay, this is where I'm aiming at, and this is an implementation of the real numbers in my own library that I developed since ages. Okay, to get an idea of what's happening behind, how can we do this? So this is the core of the program before. We have some iteration, we have some arithmetic operations. So what we could do is we start with 0.5, we have a few other values, 3.75, and the 1 here, the 1 minus, and we have to combine them, and this gives us some diagram. And we do this again for the next step, and again for the next step. In a certain way, the result of this program is this diagram. So we could use the diagram as a representation as well. With a few problems, perhaps. We want to see the result. So this means you would not be happy to have this as the result of the computation. You would rather like some decimal value at the end. So somehow you have to evaluate. First of all, this is a nice structure these days because you simply can add nodes. It could be a node instead of multiplication. It could be square root. It could be a node telling you integrate a differential equation as a simple node. So it's you can do a lot until you get to the end where you need the values. Then the hard stuff starts. This computation is lossless. You don't lose anything about your computation. You have all the information still there, which means on every step of computation, you add a little bit of memory. Let's say about 50 bytes per node that you have in this structure. It should be surely more. So let's do some real computations. A billion operations would need 100 gigabytes of main memory in your computer. It's not really useful in practice, so we will do something else. First of all, this is nice to use and to evaluate. Usually you could use something like multiple precision intervals, MPFR, and the values could be approximated, but only on demand, and you can do it bottom up, top down, whatever you like. The interesting thing is data structure is exact. And then there are, maybe you shouldn't do it this way. Maybe you should do it in a different way. I found a nice paper by Joris van der Hoven. Relax, but don't be too lazy. Don't do all this lazy stuff all the way. Or there was another nice sentence yesterday by someone, better be sloppy and fast than precise and slow. So maybe there are better ways to do this, and this would be correct as long as we don't make mistakes. As long as everything is correct, it's nice. Okay, do the same thing again. Now we are eager. We want to get the results immediately, so we start with some interval. We are sloppy, start with some interval. We continue with the computation. Intervals grow. We continue, and they grow, and perhaps, so this is exaggerating, perhaps at the end we just have one decimal left. And now we want to put the output, and we want to have it to 3 decimals. We are in a problem, so what can we do? Okay, let's do it again. The idea would be, let's do it again. Now put more effort into the thing, do the same again, and we get a more precise result. This would allow us to give us the first 3 decimals, plus minus 1 unit in the last place, something like this. So we are lossy. This is good for memory. Forget what you don't need is very important. We have to iterate things. Exceptions are what we use as a thing behind that, and there are a few of technical things. I won't go into details there. It's something sometimes a little bit nasty to do this in C++. Maybe other languages would be better, but I still want to sell to humans, so there might be a problem. Okay, we have a real data type, real, which could be fine for real numbers, eager or lazy, and we could extend this to further spaces. Is this an easy question or trivial problem? Of course, first you say no. It's complicated, but I say, I'm just thinking about vectors. Then you would say it's easy to do. We have some dependent data type, vector of real, perhaps. Or we want to have complex numbers. Okay, complex numbers is also trivial. So these are the simple things, perhaps they are the simple things. Then we get into sequences of real numbers. It starts to get complicated. In C++, we have some possibility to define functions, or you have functional languages. It's not essentially a problem. We can have functions from R to R, maybe partial functions, or we could have polynomials, we could go to analytical functions, whatever you want to do. And so we want to have more than just the real numbers. And the question is how to implement. Lazy, eager, or perhaps mixing the things. So in my library, I mix the real numbers, so then the intervals, and then the complex numbers, they are eager, the rest is lazy. Which means even though we are lazy and don't lose information there, we lose information on the real numbers, so we really, even lazy, we have to iterate our computations, because we are, in parts, we are lossy. We can go to higher order things, and I need this just because we have a differential equation example at the end. So one thing could be we have sequences of real numbers, and we are interested in the sum function if this is considered as a Taylor series. And from computable analysis, we know that, okay, this is nice to define f as the sum, but to evaluate f, we need more information. We need information about the radius of convergence and some upper bound on the area of convergence, on the disk of convergence in a certain way. Then we can compute a little bit and we get nice truncation error bounds, which are not too complicated. They just consist of this bound m, the radius, or lower bound for the radius r, the actual value x, and a little bit computation around this. Which now allows us, if we have a, r, and m, to compute the sum function. Not computing the sum is not problem, but evaluate the sum, that's the problem. We can do this. So we get some operator for an infinite sum in our system, which is, of course, non-algebraic, because we can get non-algebraic things. I will just show you the code for a simple example. Power series always 1. And we sum up, and then we end with 1 over 1 minus x. So there are always simpler ways to get the sum function than to take the Taylor series. And in our programming library, this would be, we have to define the sequence. For example, always the real 1. Then we have some real numbers, the bounds r and m. From this, we can construct data structure for the function, which is just the Taylor sum of a, with knowing that r and m are there. And then we can evaluate. And this would work. It would not work too fast, but later we will see that it still works reasonably fast. Yes? This means we have a function from int to real, and this is initialized with this procedure. Somehow we need constants, functional constants. And yeah. Yeah. So this is some procedure. So this is the constant function. Yes. So maybe I should switch to this lambda notation even in C++. I'm not sure about that. I'm old-styled. Okay. So this way we can compute a lot of things. And I presented this at a workshop in Novosibirsk, and then there was someone from interval community, and he was almost crazy about what I did, because he said, this is last century, last centennial. You need to have Taylor models. Okay, then I had a look into that, and he was right. My apology is, when I started this, Taylor models did not yet exist. So they came on the side, and now I'm implementing this later on. Okay. And we want to generalize them directly. So let's have a modified view on the computations. So go back to the representations. And don't use a single real number. Concentrate on, let's say, vectors of real numbers. So let's say we have a vector of real numbers as a state in some computation. And we compute some function. This would be the upper level in this diagram. We compute from some vector to some vector to some vector. And finally, on the real numbers, we are finished here because then some component in this vector is precise enough. Okay, this is what the user would like to see. On the lower level, of course, this vector is complicated. It's the image of, let's say, the represented number by a sequence of vectors of intervals, something like this. So let's draw them here. So in effect, this is what we have. And from this, we have to compute the next sequence of intervals, and the next one, and the next one. And finally, maybe the ON2 tells us all the information that we need to stop our program. This would be the, how we do this could be eager or lazy. If we do it in the eager way, like the iRRAM does it, we just pick one of those rows here and try to follow just a row, just not from 0, 1, 2 to 2, but just from 2 to 2 to 2 to this one. Forget about the rest. This saves you a lot of memory. Maybe even money, because you can work with cheaper computers. So we stay on a single line, which means now we compute from vectors of intervals to vectors of intervals, to vectors, and they are simple intervals. Okay. We always have that we want to compute this function on the top. So which means that we have some consistency that's necessary, that if we take just one of these vectors of intervals and apply the function, the idealized function on top, it must be a subset of what we have on the next row. And so here we have open intervals. Here we have open intervals, at least like Weihrauch defined it. And even Ulrich had some, in a certain way, problems with the open intervals. He had some representation with closed intervals, but he had to be very careful with the endpoints. That was where he had the undefinedness, the bottom things. So maybe better avoid this. But we have another problem then. The images of these boxes, open boxes, they aren't boxes again. And to show this, just let's have a look at a quite simple function. F of xy is x squared minus y squared and the product. So this is from vectors to vectors. And we start with this rectangle. And then we apply these results. And this is not a mock-up. These are the values that arise. So this is this nice structure there. But now, if we think in the traditional way with interval arithmetic, this means we have to put a box around that. And then obviously, there are empty regions. We don't want them. It would be nice if we could avoid them. And we will see later these effects that we get empty regions. Now we apply the same again, for example, and these will grow, this wrapping around. We need something which wraps around the blue structure here and doesn't have too many holes, because then we need too much paper to wrap around. So these effects unfortunately accumulate. So what we should do is we should try to avoid or reduce them. It would be nice if we could do the wrapping in this way. Then we wouldn't lose more information than necessary. So how can we do this? How can we do this? We will use Taylor models there, but let me start with something more general. We could think, instead of having just vectors of real numbers, we could have vectors of arbitrary dimension, or we could add some complex numbers or functions from the reals, or who knows what we could add as the state of the program. So the following later with the Taylor models is just an example of how we could do this. I don't have an idea what the best thing would be for such a structure. I only concentrated on the top line, the real numbers or vectors, but maybe there is more to do there. So the usual approach to such topological spaces would be effective topological spaces. We have the space, we have a subbase of the, or we have a set, the subbase of the set in some topology, and a way of enumerating them. and then we have the sequences there, which means we always are in the similar way with this original Weyrauch approach from going from open sets to open sets, which is nice because the pre-images of open are open, but we compute the other way. We compute from something to something, not to the pre-image, but we apply continuous functions to open sets, which is not that good because then we have to overestimate. And this would be, so Weyrauch CD would be doing this. And if we have product spaces, we use product representations, which means from the single intervals we go to the boxes, more or less. Okay, let's now try something, a representation for such a set, which is nice, going directly there and don't using this topology directly. Indirectly we will need it, but directly we don't need it. So now we come to something which could be a generalization of what Taylor models might be. We have a countable family of sets. They are subsets of some basic set M that we want to compute on. And we have a few properties. And the properties are every value of the set, how complicated it might be. For every value and every precision that we want, we are able to find, there is, we are not yet in computation, there is a set capital A such that its diameter is quite small and that X is in the interior. This essentially means for every single point, we are able to wrap around a single point with a very small region. And if we have such a countable family, we can define representations now as sequences of this family. And we might say that a sequence of such capital A denotes X if the sequence satisfies that the diameters go to 0 and at the end it's a point. So it's more or less a quite obvious generalization, but we avoid the product spaces and so we go directly to the points, to the elements of the set. If we take vectors, we could use boxes, okay. We could use open boxes, we could use closed boxes, we could add point intervals. Usually we start our computation, our constants, usually are rational numbers, and the first step from the rational number to the first open interval is already losing a lot of information, so let's stay with points as long as possible. We could have some unions of boxes and we must be somewhere in the union, which would be more or less interval thing. We could have DAGs, for example. So compute with DAGs, each DAG represents in the, unless we are doing something totally lazy, they could represent sets and not just points, which is an entry into symbolic representations of numbers that we could work with. And of course, we could use Taylor models, and I will explain later what this is. Now, there are many ways to do this. And if we compare those ways, if we have two ways of representing elements of M, and both of them are wrapping, they have this property that we get arbitrarily close to a point, then they are already topologically equivalent. So they are not so different, and the idea is not too complicated in the proof. I will skip the idea. Essentially, it's just what I will tell you the idea and skip the details. The idea is just we must be able to get from a set in the original A to a set in the target B somehow that the diameter of the target is the smallest possible diameter that we have in the target. There might be no minimum, so we have to add a little bit. So if we have, we can show that at least such a mapping from A to B exists, maybe not computable, but exists, and then we can compute like we did it on the with the iRRAM on one line. and don't need information around. This thing is what we would define as continuous. Everything is staying on the line, and it's realizing just identity. So more or less, this is a definition of some constructor in C++ where we construct a number in data structure B from a number in data structure A. This would be the interpretation there. We can do it in a computable way. Then this function mapping A and the precision to B should be computable. It should be multivariate. We don't want to go in all the nasty details of the computation below. And if we do this, then we even get computable reducibility. So in the usual settings, we even have computable reducibility or computable equivalence between all these types, which means, let's go back, which means it's not important how we do it, as long as it has this wrapping property. It's not important how we do it, everything will be computably equivalent, which means for computability, it's irrelevant what we do. Maybe it's irrelevant for complexity, and for sure it's relevant for efficiency of the implementation. Okay. Efficiency is the point that we are aiming at, because everything might be equivalent. And for later, we should keep in mind that in a usual imperative language, we just change one component of the state space at a time and leave most components intact. So if we have some state space x1 to xn and apply a function, then usually this function just changes one component. This is why I will only have a look at that later. Okay, I said, so in general, we can do this in quite arbitrary spaces. For real numbers, there are these Taylor models. I think most of, let's say 2/3 of you know what the Taylor models are. So let me explain a little bit for the other third of the audience. So the idea is we want to have a representation of vectors, and we start with some initial set with a hypercube of dimension k, unit hypercube, which from -1 to 1. We just define some symbols called error symbols, and we just know that they should be from this set -1, 1. We have k of them, so we're working with a domain which is u to the k. And then we take polynomials on these error symbols, multivariate polynomials, perhaps even a vector of multivariate polynomials, and so a sum of coefficients which are vectors of these parameters. So coefficients would be vectors. As a simple example, dimension 2, we want to address dimension 2, so pairs of real numbers. Our error symbols, we just take 2 of them, so in this case they are the same. And let's just take this polynomial with these 4 coefficients, the basic coefficient, and then it's lambda1 times lambda2 in the y component, and the x component it's 0, and so on. If we take this and map it, then what is the result if we apply t to the unit square, so this hypercube here, then it will give us exactly the set that we had before. This means if we take this idea of using Taylor models, we are able to get more precise values in our computation. It's just we shouldn't work with simple intervals anymore. We should work with polynomials of intervals. And of course, we know how to work with polynomials. And if we have a look at this from the idea of wrapping families, we just take all these polynomials, or take polynomials, apply them to the hypercube, and this gives us a set, and this would be the set in this wrapping family that we need. Okay, in practice, what would we use? In practice, of course, the coefficients would be double precision, usually. This would be would be fine unless we do some theory. In the theory, we need dyadic numbers or rational numbers or perhaps computable real numbers or computable complex numbers. Everything will, as soon as we are really in wrapping families and not in this finite area, everything will be equivalent again. And maybe even the coefficients could be intervals themselves, which would also be quite nice. In practice, when we have double precision coefficients, usually one coefficient, the basic coefficient, is treated as an interval of double precision numbers. It could also be it could be a point, and then we have an additional error symbol just denoting this. So we don't need intervals at all, but it would be nice to use them. And then there are many variants. We could have a fine arithmetic, order 1, so the polynomials are not too high, and only one interval. The basic coefficient is an interval. We could have some generalized interval arithmetic, which means order 1, and all coefficients are intervals. I think this is quite old already in the definition. We could have the Taylor models like they are defined in Makino and Bert's papers. We have arbitrary order, and only the basic coefficient is a non-point, is an interval. Or we could even have arbitrary intervals everywhere. Whatever we do, from the viewpoint of computability, they are the same. The question is, how fast will things be? If we compute with them, essentially we have to transform polynomials. We have to apply transformations to polynomials. So, for example, if we want to add or subtract numbers, it would be a polynomial addition or subtraction, and I want to show you the result here in a simple example to see how this overestimation will arise. So suppose we have some x, we have some y, we compute the sum, and then we subtract again. And if y is x plus y, and we subtract x from the sum, it should be y again at the end in x. Okay, let's do this. Let's assume it's dimension 2, and we have a Taylor model with two variables, two error symbols, and let's assume we start with these intervals. As a Taylor model, this could be, let's assign one error symbol to y, assign another error symbol to x, and then it would be this Taylor model. And this would be the set that we have. So the red-blue one here in the middle, the red one for the intervals, the blue one for the Taylor models. We could do some operation. On interval level, this would mean we have to add the intervals, which is not, y is now just the sum of these, which is obvious. In the Taylor models, we would also add those things. So add the first row to the second row, and it will give you this result. And if you look at the denoted values, the interval now says our pairs are from this red rectangle, while our values really are from the blue structure here, which is definitely much smaller. And when we do it again, subtract, now it should be y again, but our intervals, you see, they grow. In the Taylor model idea, we just have to subtract now the first line from the second one. And this gives us this structure again. And you see here the area didn't change in the blue structure, but in the red structure, which is interval computation, it blows up more or less. In this case, everything is fine. So what can we do? We can do multiplication, for example. We have polynomial multiplication, no problem. But the degrees will grow if we multiply polynomials, okay? And we can have further functions as long as they are Taylor series. With the Taylor series, we can truncate the Taylor series. We have a remainder, and which means somehow we will have an error if we compute with Taylor series, so accumulate this error in one of these intervals that we have. Or we add some new monomial and a new error symbol equivalently. Okay. The degrees grow, they grow fast, so we need something to get the data structure small. Usually this is some kind of rounding, and there is not clear how to round here. So one thing is called sweeping, and sweeping reduces the degrees that we have by replacing error symbols with intervals. So suppose we do some multiplication of linear polynomials, then we have mixed terms, and we don't want the mixed terms, the order is too high. We know that each of the variables is between -1 and 1, so we could replace this monomial either by c times the unit, which means one interval, or we could replace it by c times unit times and keeping lambda 1, or we could keep lambda 2. We have a lot of degrees of freedom here, and I do not know what the best thing to do is. And this is reducing degrees, and from time to time it's necessary to induce new error variables. We could do this simply by changing some coefficient, which is really an interval, by replace it by the center of the interval plus the radius of the interval multiplied by some new error symbol. And we could do this everywhere. Essentially, we want to be things simple later on. So maybe we first sweep, get rid of many of the error symbols, and then introduce new error symbols. So more or less what we do with these operations is on the level of real numbers, identity function. We just apply the identity function but change the representation, and the data structure is reduced. So we implemented this. So we implemented the most simple way. Order 1, just linear things, but with interval coefficients. So it's generalized interval arithmetic. Now we have currently 2 data types, the old data type for real numbers and the new one for the Taylor models. And we can compute or construct one from the others, compute the identity on the real numbers. So if you have a Taylor model, sweep everything into an interval, then we have an interval. Or if you have an interval, just take this as a polynomial of order 0, which be simple things. And if we compute now, addition, subtraction is not a problem, but multiplication will give us soon things with order larger than 2. Then we reduce the degree with sweeping to linear automatically. And this polishing, which means stronger change on the data structure, it must be triggered manually. Our current version, it was simple to integrate. We just had to switch somehow, or we already had intervals, so we just had to add basic operations, and it was around 500 lines of code, not more, to do this. A few examples. Let's have a look again at this crazy logistic map. What do we have to change in the code? Not too much. Instead of working with real numbers, we work with Taylor models. And from time to time, we polish the data structure so that it gets nicer. And have a look again at these orbits. And have a look now at the time. For example, if our number is 3.125, which is here, just 2 points in the orbit, if we compute this with the old version of the interval arithmetic and want to have, let's say, coefficient 100,000, we would need 175,000 bits intermediately, which is a lot and quite a lot of time. If we do this with the Taylor model, double precision is sufficient. So we stay on the lowest line of computation just with double precision. We don't have to go to higher. And it adapts to what we need. There are things like, for example, 3.82. It would take us 200,000 bits for intervals, but it takes 70,000 bits for Taylor models, or 57,000 bits for others. So it really adapts nicely to this thing. And on the top level, we don't see a lot there. And this simple linear models were sufficient there. Okay, this is a logistic map, which already shows that we get tremendous gains in computing time, and even gains in the hard cases, where things are complicated. we were trying to apply this to differential equations. Especially we had this differential equation, the van der Pol oscillator order 3 as an example. And here you see how it behaves if you started with this parameter alpha as 3 and start at some specific value. So it oscillates in a nice way. We want to solve it. One thing, we could solve it in a discretized version. So we just take some Euler method, and every 0.01 we add implement the iteration. The discretized solution is a little bit different from the exact solution, as somehow the frequency is different. I don't know why, but it's different. Okay, let's have a look what happens if we implement this. Again, we would have an ordinary implementation. We just need at 2 places to change things. Instead of a vector of reals, we would have a vector of Taylor models, and we would have from time to time, perhaps after every iteration step, we would polish things. And then what happens now? Again, a similar thing. So if we go, let's say, integrate up to T1000, we would need 14,000 bits with real numbers instead of the Taylor models. But 136, a little bit more than double, would be sufficient to do this with Taylor models. So again, a big increase in a big gain that we have. And now let's try to do the van der Pol oscillator in an exact version, which means somehow we have to solve ordinary differential equations, which is not really trivial. But also not too complicated, it can be done. So we go back to the Taylor series. At least for this differential equation, the right-hand side is quite simple. So we can just use a Taylor series approach. Just remind you that we somehow need this R and M, and to get the coefficients, if we have them, then we can have an operator for infinite summation, which is even transparent for Taylor models, because we can do the following thing. We just add or compute a partial sum of the Taylor series up to some n. And these operations are simply implemented as Taylor model operations. So we will get a Taylor model at the end. And the error is approximated as I told you before. And as soon as the error is small enough, we stop this. And then we have a Taylor model here and some error here. And we just take this Taylor model from here and add this error as a small interval to this. So it's really transparent. So we get a lot information through the Taylor series computation to this infinite operator. And now the things that changed from the previous example would just be replace real by TM. That's all that we have to do. It's just another representation for real numbers. If we want to do this integration of ODEs, we work in steps. We start with the initial condition. We do some recursion on the coefficients, which gives us a Taylor series, of course infinite, so this has to be lazy. We can do the summation, which also is lazy. It's just telling this is the sum of the things. Here we need the radius and this number m. And then we can evaluate the thing and get a new initial condition. And we work in this circle until we are there. Essentially, it's this. We start with some point. We get some radius, which means the function, the solution is defined partially here. We take some point there and evaluate it. And then we can again compute a radius and get an extension of the function and so on. We take a point, take the radius, extend, and so on until we are where we want to be. This can be perfectly done with these simple right-hand sides in the ODE. Unfortunately, the radii of convergence always are finite, so we cannot do this in very large steps unless the system is even linear. It looks like analytic continuation, but it's much simpler because we always get back to these initial conditions in between, and that is a place where we can do this polishing of the data structure. So here we polish our initial value is Taylor models. Then we do the recursion. Our power series has Taylor models as coefficients. And then in the evaluation, we get again a Taylor model, and we can polish this. Now, if we do this, the first thing is we need to get the radii, and we spend a lot of time to do this. So our initial experiments with just Picard-Lindelöf were here. So I should explain a little bit more. So we have this solution, and if we have an initial value, let's say at 13, then we can try to compute a radius of convergence for this point 13. Picard-Lindelöf gives us something like 1/20th. We can improve this, and the best thing was some iteration of some improving method. I won't go into the details here, but we compare this with the step size in VNodeLP, which is a program by Nedyalkov for using Taylor models to solve differential equations, and they got a step size which was this one. So they didn't use our methods to compute things, but they got a comparable step size, so we are not too bad in estimating the radii. And now we can try to run this. And we can try to run this with the old intervals. This was what we did a few years ago, more or less. And if we want to integrate up to, let's say, 8.25, so the time instance would be less to the left of this thing, we would need 33 seconds, and 242 bits would be sufficient. And if we take the Taylor models, it would take us 56 seconds, so more time, and the same precision, so their Taylor models do not help yet. And then we try to integrate a little bit longer, so to 15.75, so to somewhere up to here. And then, yes, our computation with the intervals at this point 8.25, it came to an end. Precision was not enough to print 22 decimals, so we had to do an iteration. We had to start again. So we had to start again. We started with 375 bits, and now it took a little bit more time, and so on. And if you have a look here, if we continue to integrate, you see from 8 up to, let's say, 140, the number of bits is growing more or less linear in the end value, so some factor between 20 and 30 of this. The time is growing tremendously that we need. So if we have a look from here to here to here, it looks like it's doubling every step. So this looks like exponential growth of time. I think it's not exponential. I think it's just some polynomial to the order of 10 or something like this, which in practice is almost like polynomial. And if you take the Taylor models, okay, we don't get things for free, but astonishingly, we don't need a higher precision. There is really, it looks like there is a basin of attraction like with a logistic map. And somehow, as soon as we are close enough to this basin of attraction, we don't need a higher precision anymore. So we could compute or continue this computation for a very long time, integrating up to 5,000, 10,000. And sometimes it would be nice. Sometimes we didn't catch the basin of attraction. So in this case, it looks like we went into this basin of attraction, and the times then just grow linear. So this is our biggest example that we did. So really, we find the same things like orbits and dependency on initial conditions and so on. From the logistic map, we find them again here in higher dimensions. Taylor models are there, and they help as in the simple models. So still, the logistic map is a very good example if you want to do such things. And yeah, that would be more or less what I wanted to say as a content. We are still working on this. So we started this about a year ago, and we have to enhance our Taylor model versions, this transparency to the power series summation. We have to have a closer look on this also for other limit operators. Of course, we have to do optimizations, the sweeping polishing. It's so many degrees of freedom that we still do not know what the best is to do. Maybe there is no best thing. We just have to try. We have to try higher order models. Maybe there is a specific treatment of squares, which is nice in Taylor models. And of course, we want to have a precise complexity analysis of all this stuff. Can we measure can we measure this in some way that Taylor models really help? Or is it just efficiency and we see it? Or can we prove that things might be better with the Taylor models? Okay, that's it. Thanks for your attention, and I'm open for questions and remarks. One slide back, okay.
Thank you. So in a lot of real number computations, you face this dilemma which has different phenomena, but it's, should I go one line up in the iterations or should I improve the efficiency?
Yeah.
Is that sort of the analog of sweeping polishing, or is the sweeping polishing doing a different thing? And you still have also the other problem.
We still have the other problem. It's just maybe the question is, if we increase the order of the Taylor polynomials, should we increase the order or should we go one level up? That's rather the difference that we have. So if we increase the order of the Taylor models, we get each model is more complicated. We have more coefficients to deal with, more combinations, so it gets more complicated. If our functions that we compute are not too complicated, it might be simpler to compute with a little bit higher precision, and then we also get to the end. So I do not know where the trade-off is between increasing the order and increasing the precision of the single computations. And it's still, we are aiming at points here. And I know that Peter Collins is already nodding. If we are aiming at sets, computing with sets instead of computing with points, things again look completely different. And then we have to rethink again. But here, sweeping polishing optimizes a little bit what we do on a single line, but it's rather whether the decision is whether to take a higher order or to take higher precision to get to the next line.
I think I can well imagine a user who is going to put in randomly the sweep polish thing is just until he finds a combination that works best, right?
I fear currently, yes. We don't have good heuristics to do this. For this ODEs, of course, whenever we get back to an initial value or to a state where we do the iteration again, that's a place to polish. Whether it's a good idea to polish in between, I do not know. And the sweeping has to be done automatically in between, because otherwise multiplications will kill you soon. Very soon.
Thank you.
Which strategies do you use for polishing?
Okay, now it starts to get complicated. We have a lot of intervals there. We have the intervals for the base coefficient and for the order 1 coefficients. Okay, whenever so we test whether it's necessary to polish. So we don't always change things. It's just when the initial, so the order 0 coefficient, which is an interval, as soon as the width of this interval is comparable up to 20, 30 bits to the size of the center, then it's a good idea to start. And whenever the sizes of the order 1 coefficients are similar to the radius of the order 0, then it's also an idea to start such a polishing process. And then we don't polish a single value, we polish the complete data structure, all of them, to get rid of many of the error symbols and introduce a few new. Currently, the last implementation was we get rid of all of the error symbols with respect of the two largest for each variable. And then we introduce one new, which would mean in this dimension 2 process, we would have up to 6 lambdas, 6 error symbols at the same time. And then we reduce them again and add new ones.